Could a state-of-the-art AI actually hack a corporate network all on its own? It's a question that's jumped right out of science fiction and into some pretty serious national security talks. But if you get past the headlines, how do we really know what these models are capable of? Okay, let's dive in and see how researchers are trying to figure that out.
So, what you're seeing here, this isn't just some abstract graphic. This is a frontier AI model, live, in the middle of a multi-step cyber attack. We're talking about a whole chain of events, finding its way around, exploiting weaknesses, moving through a network, all happening inside a simulated company. This image from a paper by Folkerts and colleagues is really our jumping-off point.
So, that's the big question, right? How do we even get this data? It's one thing to see a cool graph, but it's another thing entirely to understand how we measure this stuff. And that's what this is all about. How do you rigorously test an AI's ability to pull off an attack? And how fast are they actually getting better at it? To get to the bottom of this, we're going to walk through it step by step. First, we'll look at the evaluator's toolkit, all the tests researchers are using. Then, how a model even becomes an agent in the first place. We'll check out the scorecard on current AI abilities, but then, and this is key, we'll hit pause for a big reality check on what these tests aren't measuring. And finally, we'll look at what's on the horizon for testing these incredibly powerful systems. All right, first up, the evaluator's toolkit. Now, testing an AI's hacking skills isn't just some simple pass or fail exam. Researchers have had to build a whole range of different benchmarks, and each one is designed to test a different piece of the puzzle, from basic book smarts to complex real-world strategy.
And these methods have really evolved fast. They started out with simple question and answer tests just to see what the AI knew. Then they moved on to these gamified puzzles called Capture the Flag Challenges, or CTFs. More recently, we've seen AIs tasked with reproducing old, known vulnerabilities. And now, the real cutting edge is these super complex cyber range simulations and even live penetration tests on enterprise networks, stuff that looks a lot more like the real world.
Okay, let's unpack that a little. You've got your CTF challenges, like SciBench, which are great for testing one specific skill in a little puzzle box. Then you step it up to something like the 3CB benchmark, which was designed to assess what they call catastrophic capabilities, skills that map directly to real-world attack techniques. Then you get even more complex with multi-step scenarios, like the last one's network we saw at the start. And then, at the very top, the most realistic stuff we have are frameworks like Artemis that actually pit AI agents against human experts in a live environment. So we have all these different tests. But how does a language model, which at its core is just predicting the next word, actually do any of this stuff? Well, the secret sauce is turning that model into an agent. And that happens through something called agent scaffolding. As we and their colleagues explain it, this is this whole structure of code you build around the AI model. Think of it this way. The model is the brain, but the scaffolding is what gives it a body. It gives it a goal, a way to plan, a memory of what it's done, and this is absolutely critical, access to a whole toolbox of real-world hacking software, like the stuff you'd find in Kali Linux. That's what turns a passive chatbot into an active cyber attacker. Okay, now that we know how they're testing these things, let's look at the results. What have all these evaluations actually found? Well, when you pull together all the research, the picture it paints is one of just incredibly rapid progress. And these two charts just illustrate that perfectly. They show the two main things driving this progress. So, the chart on the left, that shows that performance gets better with more compute. Basically, if you just let the AI think longer, it gets better at completing the attack. Now look at the chart on the right. This shows that newer models are just inherently better. Just look at that massive jump from Opus 4.5 to Opus 4.6 in only a few months. That's a 42% improvement in the number of attack steps it could complete, according to the Folkerts paper. So what does that actually translate to in, human terms? Well, get this. The researchers from that same paper estimate that a human expert would need about 14 hours to pull off their simulated attack. The best AI run from Anthropic's Opus 4.6 model managed to complete a chain of steps that would have taken that human expert about 6 of those 14 hours. That is a huge leap in what these things can do on their own. Now, we have to be specific here. A 2024 study from Anthropic and colleagues makes it really clear that these powerful offensive skills are pretty much concentrated in the big, proprietary frontier models. Your smaller open source models, for now at least, they show much more limited abilities on these tough benchmarks. And the AI labs themselves are all over this. Take Anthropic, for instance. They have this formal, responsible scaling policy that basically says they won't deploy a new model until it passes specific safety tests.
Their internal red team has found that their top models have pretty much maxed out what the public CTF-style benchmarks can even measure. And get this, their specialized model, called Mythos Preview, has apparently been used to find thousands of zero-day vulnerabilities. And just to be clear, those are security flaws that nobody knew existed before.
Okay. Now for what is honestly the most important part of this whole explainer, the reality check. The results we've seen are, they're startling, but they all come with some massive asterisks, because a lab, no matter how good it is not the real world.
You have to read the fine print here, and the researchers are super upfront about this. In almost all these tests, there's no one fighting back. There are no modern security tools like EDRs. There's no incident response team trying to hunt the attacker down and kick them out. The attacks happen over a few hours, not the weeks or months a real campaign would take. And maybe the biggest one, most of these tests just assume the attacker has already gotten into the network.
So let's just draw a really clear line. What have we actually seen demonstrated? The ability to exploit known vulnerabilities by itself and chain a bunch of steps together in a simulated, undefended network. What's still a huge question mark? The ability to get past a live professional security team to full sophisticated software and to run a full campaign against the target that is actively fighting back. That's not a small gap. That is a massive gap.
Which brings us to the final piece. So where do we go from here? What does a truly realistic test even look like? And how can our ability to measure these risks possibly keep up with how fast the AI itself is developing?
Well, according to researchers like Wei and their team, the next big step is to move towards what they call dynamic risk assessments. This just means we have to stop testing the AI out of the box. We have to start modeling what a determined attacker with time and money could do to actively fine-tune and improve the AI for a specific mission. They actually showed that with just a little bit of extra compute, an attacker could boost an agent's performance by over 40%.
And this isn't just some academic theory. Governments are already moving on this. The UK's AI Safety Institute has flat out said that their future work is going to include exactly what's been missing: hardened, defended environments with active monitoring, security software, and real-time incident response. In other words, they're getting ready to test these AIs against a defender that actually fights back. And that leaves us right here with the central question. We are in a race. On one side, you have AI capabilities just accelerating at this unbelievable rate. And on the other, you have our ability to build realistic tests and effective safeguards that are desperately trying to keep up. The challenge isn't just about what an AI can do today in a sterile lab. It's about whether we can stay ahead of what it might be able to do tomorrow out in the real world. All the research we talked about today, from the academic papers to the government reports, is out there for you to read. So for anyone who wants to dive deeper into the data and the methods, these are the sources that we built this explainer on. Thanks for watching.